There is a deeply seductive story that human civilization has been telling itself for decades now. It is the story of the red planet as a destination, a waypoint, a second home waiting just beyond our current reach. Missions are planned with extraordinary care. Trajectories are calculated with breathtaking mathematical precision. And somewhere embedded in the confident architecture of these plans sits a quiet, almost invisible assumption that tends to escape serious public scrutiny. The assumption is this: that a vehicle built on Earth, launched across hundreds of millions of kilometers of interplanetary vacuum, lowered through a paper-thin Martian atmosphere, and then left completely alone on the surface for anywhere between 14 and 26 months, will still be perfectly capable of igniting its engines and hurling a human crew back into orbit on demand. That assumption is where the physics breaks down. That assumption is where the thermodynamics turn brutal. And that assumption, when examined with genuine scientific rigor, reveals that returning from Mars is not merely difficult. It is, under current engineering constraints, a sequence of compounding physical catastrophes that would almost certainly consume anyone who attempted it. To understand why, we have to begin not with rockets, but with time and entropy. Because the single most destructive force working against a Mars return vehicle is not the launch itself. It is the slow, relentless, invisible degradation that accumulates across every single day. The vehicle sits idle on the surface, waiting for the orbital geometry to align favorably enough to make the journey home possible. Consider a precise analogy that strips away the romance of space exploration and replaces it with cold mechanical reality. Imagine taking a highly sophisticated, ultra-precise mechanical engine. Strip away its protective housing entirely. Now place that engine inside a hyper-dry, aggressively static sandstorm and leave it there for 2 full years. No mechanics visit it. No spare parts are available. No fresh lubricant is ever applied. The sandstorm never stops. The temperature swings violently between deeply negative values at night and comparatively warm temperatures during the day, repeating this thermal violence hundreds of times without pause. After 24 months of this continuous microabrasion and chemical oxidation, someone asks you to instantly start that engine at absolute maximum capacity because a life depends on it. You know from basic material science that the internal seals are compromised. You know the valves have seized from repeated thermal contraction cycles. You know the corrosive chemistry has eaten into the fuel system. The engine does not save you. It violently detonates. That is precisely the unyielding operational reality of attempting to launch an unserviced ascent vehicle off the surface of Mars. But let us build this understanding from first principles, because the physics here is far richer and far more merciless than any single analogy can capture. The Tsiolkovsky rocket equation governs all of this. It is perhaps the most brutally uncompromising relationship in all of applied physics, and it was derived over a century ago with a mathematical elegance that still feels almost painful in its simplicity. The equation tells us that the velocity a rocket can achieve is proportional to the exhaust velocity of its propellant multiplied by the natural logarithm of the ratio of the rocket's initial mass to its final mass. That mass ratio, the fraction of the total vehicle that is pure propellant versus the fraction that is useful payload, is the central, inescapable battlefield of rocket engineering. Mars has a surface gravity roughly 38% that of Earth. Its atmosphere is approximately 1% the density of Earth's atmosphere at sea level, which means it provides almost no aerodynamic assistance during ascent. A vehicle leaving the Martian surface needs to reach orbital velocity of approximately 3.4 kilometers per second just to reach a stable orbit. And it needs to do this while carrying human passengers, life support equipment, and enough supplies to survive the journey home. The rocket equation responds to these requirements with merciless arithmetic. The vast majority of the vehicle's total mass at launch must be pure chemical propellant. The payload fraction, the actual humans and their survival systems, ends up representing a tiny percentage of the total mass stack. Now introduce the idea of protecting that vehicle from the Martian environment during its long surface stay. Every kilogram of protective metal plating added to shield the engines adds to the dry mass of the vehicle. Every kilogram of additional insulation wrapped around the fuel tanks adds to the dry mass. Every additional sensor, every redundant valve, every reinforced seal adds mass. And the rocket equation is logarithmic in its punishment. It does not scale linearly. Adding protective mass to the return vehicle does not simply require a proportional increase in fuel. It requires an exponential increase. The mass that must be launched from Earth to deliver the vehicle to Mars in the first place grows far faster than the protective measures themselves. At some point, the mathematics of the initial Earth launch become physically impossible to satisfy, not because of insufficient engineering ambition, but because the rocket equation is a physical law, not a design parameter. So the engineering community faces a fundamental trap. To protect the return vehicle adequately requires mass. Mass requires exponentially more propellant. More propellant requires a larger, heavier vehicle. A larger, heavier vehicle requires even more propellant to deliver it from Earth. The trap closes on itself. The solution most commonly proposed is to leave the return vehicle relatively unprotected and hope that Mars is gentler than the physics suggests it will be. The physics disagrees with that hope profoundly. Now let us move to the thermodynamic dimension of this problem, because the propellant question alone is enough to reframe the entire enterprise, and it becomes even more severe when we examine what happens to the fuel itself during the surface wait. High-performance chemical rocket engines capable of producing the thrust necessary to lift a crew off the Martian surface and reach orbital velocity do not burn conventional liquid fuels at room temperature. The most energetically efficient propellant combinations currently available involve cryogenic liquids. Liquid oxygen, which must be maintained at approximately minus 183 degrees Celsius. Liquid methane, which must be maintained at approximately minus 161 degrees Celsius. These temperatures are not preferences. They are physical requirements. If the temperature of the propellant rises above its boiling point, it transitions from a dense liquid storing enormous energy in a compact volume into a gas that expands and escapes from the storage tanks continuously. This continuous loss of propellant is called boil-off, and it is driven by nothing more exotic than the second law of thermodynamics. Heat always flows from regions of higher temperature to regions of lower temperature. The Martian surface, even at its coldest, is vastly warmer than the cryogenic temperatures required to keep the propellants liquid. No insulation system is perfect. No vacuum jacket is infinitely effective. Heat will leak into the tanks. It does so slowly and persistently, and it does so every single day across the entire surface stay. The orbital alignment windows that make a return journey from Mars to Earth energetically feasible occur roughly every 26 months. A crew that lands on Mars near the optimal departure window will typically wait somewhere between 14 and 18 months before the geometry of the solar system allows them to make the return trip without requiring prohibitive amounts of additional fuel. During those 14 to 18 months, the cryogenic propellant is fighting a losing thermodynamic battle against the Martian thermal environment. Each day, a fraction of the propellant boils away. Each day, the fuel reserves that the rocket equation requires are quietly diminishing. Over a surface stay of 500 days, even a boil-off rate that sounds trivially small on a per-day basis accumulates into a catastrophic total loss. The return fuel literally evaporates into the dead Martian sky, leaving the tanks dry before the departure window ever opens. Active refrigeration systems can theoretically mitigate this boil-off, but active refrigeration systems require continuous electrical power, and they themselves are mechanical systems with moving parts, seals, and thermal interfaces that degrade over time in the Martian environment. They add mass, which the rocket equation punishes. They add complexity, which entropy punishes. They add maintenance requirements that cannot be satisfied without a human ground crew. And this brings us to perhaps the most viscerally destructive physical reality of the Martian surface, one that receives far less attention than the rocket equation or cryogenic thermodynamics, but that may represent the most immediate and practically insoluble engineering challenge of all. Martian soil is not passive dust. It is not the benign, inert grit that might accumulate on a vehicle sitting in a desert on Earth. Martian regolith is deeply saturated with chemical compounds called perchlorates, highly reactive oxidizing agents that are profoundly corrosive to organic materials and metallic surfaces alike. Beyond their chemical aggression, the particles of Martian dust are shaped with a microscopic jaggedness that differs fundamentally from the rounded, smoothed grains produced by liquid erosion on Earth. Martian dust is sharp, angular, and abrasive at scales that matter enormously to precision machinery. And because the Martian atmosphere is so thin and the surface is continuously bombarded by solar wind particles, the dust carries persistent electrostatic charges. These charges cause the dust to cling aggressively to any surface it contacts, including metallic surfaces, rubber seals, optical sensors, and mechanical interfaces. Martian dust does not simply settle onto a vehicle and sit there passively. It penetrates. It works its way into every gap, every seal interface, every valve seat, every injector orifice. The consequences for a rocket ascent vehicle are precisely what material science would predict. Rubber seals that must expand and contract during engine ignition to contain high-pressure cryogenic propellant become brittle from repeated extreme thermal cycling and then crack along the planes where perchlorate crystals have grown into the material. Fuel injectors, whose orifices are calibrated to micrometer tolerances, become partially blocked by accumulated dust particles, destroying the precise fuel-to-oxidizer ratio that the combustion process requires. Mechanical latches and release mechanisms that must fire with perfect reliability during the ignition sequence become bound by dust that has fused with lubricants under thermal cycling. The physics here is not speculative. It is the straightforward application of tribology, the science of friction, wear, and surface degradation in mechanical systems, materials that must maintain their functional geometry across thousands of thermal cycles in a perchlorate-rich, electrostatically charged, abrasive environment will degrade. The question is not whether they degrade. The question is by how much, and whether the degradation crosses the threshold between an engine that ignites and an engine that catastrophically fails under the enormous pressures of launch. Without a human ground crew actively inspecting, cleaning, lubricating, and replacing components, the probability that every critical system across the entire ascent vehicle remains within its operational tolerance after 18 months on the Martian surface approaches the thermodynamically expected outcome, which is degradation. And here we arrive at the most sobering aspect of the entire physical picture. The failure modes do not announce themselves in advance. The compromised seal does not send a warning signal. The partially clogged injector does not display its blockage on an instrument panel. The bound mechanical latch does not reveal its condition until the moment it is commanded to release under maximum load. The discovery of these failures happens at the worst possible moment, during engine ignition, when the vehicle is already committed to the launch sequence, when the crew is strapped inside, when there is no ground crew available to intervene, and when a partial engine failure under the mechanical stress of launch produces not a gentle shutdown, but a violent, uncontained structural failure. The universe does not offer sympathy for the hubris of complex mechanical systems operating in high entropy, isolated environments. Thermodynamics is not a guideline. It is not a challenge to be overcome through determination or ambition. It is the physical description of how energy and disorder behave in a closed system, and the combination of cryogenic boil-off, perchlorate corrosion, thermal cycling fatigue, and electrostatic dust infiltration creates a degradation environment so severe that maintaining the mechanical precision necessary to defeat Martian gravity becomes, under current engineering capabilities, a fantasy dressed in the language of aspiration. Returning from Mars requires that every single one of these physical problems be solved simultaneously, not approximately, not mostly, but perfectly, because a launch vehicle that is 98% functional can still be a launch vehicle that kills everyone aboard it. The margin between success and catastrophe in rocket propulsion is not measured in percentages. It is measured in whether the combustion chamber pressure holds or whether it does not. What the physics tells us, with the same calm authority that it tells us the speed of light is constant and entropy always increases, is that we do not yet have the material science to prevent perchlorate infiltration across a multi-year surface stay. We do not yet have the passive thermal management systems to prevent cryogenic boil-off without continuous active intervention. We do not yet have the mechanical engineering solutions to maintain precision seal integrity through hundreds of thermal cycles in an abrasive, reactive environment without regular human servicing. These are not problems that enthusiasm resolves. They are not barriers that courage dissolves. They are open questions in material physics, thermodynamics, and mechanical engineering that require genuine scientific solutions before the first human crew is committed to a surface stay from which the only exit is an ascent vehicle that has been quietly fighting